In order to see the faint light from objects in deepest space, astronomers go to the darkest places on the planet. In order to listen to their quiet radio signals, astronomers head as far away as possible from radio-noisy humans. But there is nowhere on Earth, or even orbiting Earth, that's far enough to hear the faint radio hum from the time before stars. In fact, we may need to build a giant radio telescope in the quietest place in the solar system, the far side of the Moon. Putting a giant telescope on the Moon sounds like a cool idea. After all, the Moon has essentially no atmosphere, so the sky is crystal clear, and that nice stable surface means we could probably build a large telescope right there, perhaps a much larger one than we can put in orbit. People have been talking about doing this for decades, but the closest we've ever gotten is the ultraviolet scope on China's Chang'e 3 lander, with its 2-inch diameter mirror. So, is the idea of a proper giant telescope just sci-fi fantasy? Well, maybe not. Meet the Lunar Crater Radio Telescope. It's a giant radio antenna filling a crater on the far side of the Moon. If it's built, it'll be one of the largest telescopes ever built, and by far the largest outside our atmosphere. And it'll see further than any existing telescope peering into the time before the first stars and galaxies formed. And it may indeed get built. In 2020, the Lunar Crater Radio Telescope received $500,000 in funding from the NASA Innovative Advanced Concepts Program to explore its feasibility. It's going to take quite a bit more work to convince NASA to greenlight the project, but first, let's see if we can even convince ourselves that this is a good idea. First, let's remind ourselves real quick why it's nice to have telescopes in space. It's because of Earth's pesky atmosphere. For most wavelengths of light, that thick blanket of breathable transparent gas is actually a thick blanket of impenetrable fog. Gamma rays, X-rays, and most ultraviolet light is stopped in the upper atmosphere, while only narrow bands of infrared light get past the water and CO2 molecules to reach the surface. This leaves only 2 windows on Earth's surface where nearly 100% of photons make it to the ground: visible light and a section of the radio spectrum. To see most of the EM spectrum, we need to put telescopes in space. JWST for infrared, Chandra for X-rays, Hubble for ultraviolet, etc. And Hubble is even great for visible light for a different reason: it avoids the blur introduced by the atmosphere. But for a long time, radio astronomy has been left out of the space telescope game. Not only is the atmosphere transparent to a huge window of radio light, it also doesn't introduce the same blur. For that reason, we've been pretty happy building our giant radio telescopes on the surface of the Earth. So why put one in space? Well, radio photons with wavelengths of around 1 centimeter to 10 meters can pass through the atmosphere just fine. But wavelengths longer than that tend to get reflected by the ionosphere. This is where the last wisps of the atmosphere are fading into the near vacuum of space. The intense solar radiation up there separates electrons from their atoms, wreathing the planet in a shell of charged particles. When a radio photon reaches the ionosphere, it'll jiggle an electron, and that jiggling electron will send the photon right back where it came from. So our planet is surrounded by a sort of double-sided radio mirror. This can actually be handy. We can send radio signals extremely long distances across the surface of the Earth by bouncing them off the ionosphere. But it also means that from the surface, space is completely dark to long wavelength radio light. In fact, even low Earth orbit satellites are affected by the ionosphere and by the extremely radio noisy local primate population. Which means that we have literally never looked at the universe across an enormous range of the electromagnetic spectrum. That's what the Lunar Crater Radio Telescope will allow us to do. Now, while I fully support peering at the universe in new ways just to see what we'll see, that's probably not enough to convince NASA. They're going to want to be sure that we learn something important if we expand our vision that way. Well, there's always the fact that this huge blind spot in the EM spectrum corresponds to an entire cosmic epoch that we've never glimpsed. So, the oldest light that we can detect is the cosmic microwave background radiation, which was emitted when the universe was around 370,000 years old. The hot plasma of hydrogen and helium that filled the early universe back then cooled to the point that electrons and nuclei could form the first atoms, rendering the universe transparent to light. The photons released at that moment were mostly infrared. But since then, they've travelled 13.5 billion years through a universe that expanded by a factor of over 1,000. We say that the light was redshifted, from infrared to the millimetre wavelength photons of the cosmic microwave background. But after the release of the CMB, there's a huge gap in the fossil record. At some point, all that hydrogen and helium gas collapsed to form the first stars and galaxies lighting up the universe. The James Webb Space Telescope is seeing some of this very early starlight. But between the release of the CMB and the time when star formation really took off, there's a gap of at least 100 billion years. We call this the Cosmic Dark Ages, and it's crucial for understanding everything that happened after it. It was during this time that gravity began to pull matter together into the massive halos that would form superclusters of galaxies. At the moment, everything we know about the Cosmic Dark Ages comes from our simulations. But with a giant moon telescope, we could actually peer into this time and see what? If there were no stars or galaxies, what light would we even look for? The matter that would go on to form stars would then be in the form of hydrogen and helium gas that would quickly be losing the heat it had when it first formed. As such, it would emit very little light, but not no light. When the electron in atomic hydrogen flips the direction of its spin, it emits a very low energy photon of radio light with a wavelength of 21 centimeters. If you point a radio antenna at the space between the stars in the Milky Way and tune the receiver through the wavelengths, you'll see a spike in the signal at 21 centimeters. We've actually mapped the cold gas in the Milky Way by looking at this light with our big Earth-based radio telescopes. Now, any 21 centimeter radiation emitted during the Cosmic Dark Ages will have been redshifted by the expansion of the universe. For example, a 21 centimeter photon emitted when the universe was just, say, 17 million years old will be stretched to 21 meters by the time it reaches us. More distant, earlier gas will be seen at longer wavelengths still. While regular 21 centimeter radio light reaches the Earth's surface, the stuff coming to us from the Cosmic Dark Ages has been redshifted to the point that it bounces right off our ionosphere. So perhaps you're starting to see why a space radio telescope might be a good idea. Okay, sure, but why a giant one? And why on the moon? Well, the bigger the telescope, the more sensitive it is, so that's nice. But there's a more critical reason for giantness. In order to detect light of a certain wavelength, you need a telescope that's at least as big as that wavelength. And to cleanly bounce that light around in order to make an image, the telescope should be quite a bit larger than the wavelength. In fact, the resolution of a telescope depends on the ratio of its aperture size to the wavelength it's looking at. In order to get good resolution, looking at tens of meter long radio photons, you need a telescope that's hundreds of meters in diameter at least. And that does sound like a big scope. It was an enormous challenge to get JWST's 6.5 meter mirror safely into space. But mirrors for infrared, visible and ultraviolet light are heavy, fragile glass. Radio telescope mirrors can be a simple mesh of conducting material. Remember I said that the ionosphere reflects radio waves because it contains electrons for those waves to move around. Well, a metal wire has movable electrons, and so a radio wave hitting a wire mesh will just bounce off it as long as the wire grid size is sufficiently smaller than the wavelength of interest. That reflecting surface still has to be the right shape, and the right shape is a paraboloid, a circular parabola, just as with regular telescope mirrors. A paraboloid will focus incoming waves from a particular direction to a single point. Most radio telescopes swivel to the point of the object of interest, but above a certain size, swiveling becomes impractical. For one thing, the shape of the dish warps as it moves. That's why our largest radio dishes are built fixed in valleys, like China's 500-meter FAST telescope or Puerto Rico's slightly smaller Arecibo before it collapsed. Rest in peace, buddy. And just a side note, because it's cool how these fixed dish telescopes work, they have feed antennas, which is the detector, that can slide around to the focal points of light coming in from different directions. Arecibo used an elongated feed antenna to correct for its spherical dish shape, while FAST uses movable panels to warp the dish into a paraboloid pointing at the feed antenna location. The Lunar Crater Radio Telescope will be a 350-metre diameter fixed dish, so a bit bigger than Arecibo and a bit smaller than FAST. Now, this isn't a new idea. There have been proposals to build a fixed dish radio telescope on the Moon since the 60s. One of the reasons these never went anywhere is that it's not really possible to build an Arecibo equivalent there. Both Arecibo and FAST have heavy support structures to hold them in the correct shape. This requirement is one of the things that killed previous proposals. It was and still is too difficult to transport the heavy support structure required to maintain the shape of a moon telescope. But the Lunar Crater Radio Telescope has a beautiful workaround. Just hang the telescope like a giant space hammock. Normally, when you hang a thread between 2 points, you get a shape called a catenary, not a parabola. But that's only if the rope has a constant thickness. If the wires are thicker at the edges and become thinner towards the center in just the right way, that thread will hang as a parabola. So it's possible to create a perfect parabolic dish with no supports besides whatever tethers it to the edge. This design will also safely withstand the 300 Kelvin range of temperature that it'll be exposed to, a fluctuation that could damage a more rigid architecture. Although actual observations will only happen during lunar night when the radio noisy sun is out of the way and the temperature fluctuation is more like 10 Kelvin. The new LCRT design calls for the entire reflector mesh to weigh around half a ton with a total launch mass of around 3 times that, and this is well within the capabilities of current launch technology. But it's one thing to get a giant net to the moon and entirely another to set it up. Let me talk you through the current plan with this nice animation produced by the LCRT team. The spacecraft containing the folded up telescope lands in the center of the chosen crater, and I'll come back to how that's selected. Then harpoons are fired beyond the crater rim, and these are pulled tight, and then the feed antenna is raised to what will be the focal point of the dish. Then the mesh is unfolded by pulling it up towards the rim. By adjusting the tethers, the shape of the reflector can be adjusted into a nice round paraboloid. Okay, so we know how we might go about installing a Lunar Crater Radio Telescope. We just need to choose a crater. We want it to be on the far side and preferably deep into the far side to minimize interference from the Moon's annoyingly radio loud planetary neighbor. Since the telescope won't be steerable, it'll point wherever that spot on the Moon is pointing. That means it sweeps out a ring as the Moon rotates once per month. That ring is at its maximum size if the telescope is on the lunar equator. Unfortunately, that location sweeps through the Milky Way, which is loud with radio signals that we don't care about. Positioned though around 15 degrees north of the equator gives us a large circle above the galactic dish, which gives us a much clearer view of the beginning of the universe. Adding the restriction of a nice boulder clear and relatively deep crater really cuts down the options. The current top candidate is this little guy. At 1.3 kilometers across and nearly 300 meters deep, it's small enough that it doesn't even have a name. However, is large enough to comfortably fit our proposed new toy. As nice as it'll be to have the entire mass of the Moon acting as a shield against human radio interference, it does make communication with the observatory challenging. Radio telescopes in particular collect an enormous amount of data, so how do we transmit it back to Earth? We'll probably need a dedicated relay satellite, perhaps orbiting the Moon so it uploads new data on the far side and transmits it on the near side, or perhaps a relay parked at the Earth-Moon L2 Lagrange point. So, is NASA going to fully fund this? The proposal certainly seems plausible, and the science is very compelling. However, there are other options for looking into the cosmic dark ages besides specifically a radio telescope in a lunar crater. For example, there are plans to cover much larger regions of the Moon's far side in simple dipole antennae, or even build such a dipole array from a swarm of satellites that orbit the Moon or sit at the L2 point. There are advantages and disadvantages to all of these approaches, and possibly a combination is the real answer. Honestly, turning the far side of the Moon into a giant radio telescope with crater dishes and dipole arrays sounds too cool not to do. But I'm not NASA, so I'll have to wait to see what they decide is the smartest way to peer into the time before stars at the beginning of space-time. Hey everyone, Before we get to comments, we wanted to let you know about our Patreon. It's an incredibly helpful way to support the show and ensure our survival long term. If you join, there's lots of amazing perks, including monthly Q&A live streams, access to episode scripts, and even a private chat with me depending on the level. And every level includes access to our Discord, where you can interact with other community members 24/7. Another way to support the show is by visiting our merch store, where you can score some sweet SpaceTime swag. And as always, subscribing, hitting the bell notification, and joining the early gang when new episodes drop is a great way to support us. Okay, today we're doing comment responses for the last 2 episodes, the one about so-called dark stars, stars powered by dark matter, and the one about space-time foam, the tumultuous finest scale where the geometry of space is constantly changing. Starting with dark stars. DMaster254 asks whether, if dark matter can annihilate, does that mean that over a stupidly long timescale, the amount of dark matter would diminish? Well, the answer is yes, but then the new question is, what effect would this have? For example, if dark matter in galaxies diminishes, would that mean galaxies eventually fly apart due to the diminishing gravitational field? And the answer to that is that this could happen, but it would be over an unthinkably long timescale because the rate of interaction between dark matter particles is insanely low. But over time, yeah, it might cause galaxies to fall apart. That timescale depends on what dark matter actually is, but my guess is that all stars will have burned out before we get close to this happening. A few of you commented to praise John Mitchell, the guy who first conceived of black holes back in 1783, which he called dark stars, and they have no relation to the dark matter-powered dark stars of that episode. In the episode, we showed what was supposed to be a year-oldie picture of a black hole, and some of you wondered whether this was John Mitchell's drawing. The answer, sadly, is no. We just made up that graphic for fun, based on the black hole from the movie Interstellar, in which the light from the accretion disk around the black hole is warped due to the intense gravitational field. The interstellar black hole was based on real simulations that used Einstein's general relativity to calculate the deflection of light in warped spacetime. John Mitchell, however, came up with the idea for dark stars 132 years before general relativity, so had no idea about warped spacetime. His black hole, which he called dark stars, were imagined as stars so massive that their light was slowed to the point of stopping and falling back onto the star. We now know that this doesn't happen. The speed of light isn't changed due to the gravitational field, rather its energy is sapped, but that manifests as the wavelength stretching, redshifting, and in the case of black holes, a photon trying to escape from the event horizon is redshift to non-existence. But it turns out that the slowing of light gives the same answer for the size of the event horizon of a black hole as the redshifting of light. And if light slows in a gravitational field, then it should indeed be deflected by a gravitational field in the same way that light is deflected when it enters a medium like water, where its speed changes. So, in principle, Mitchell could have guessed that dark stars might look like the interstellar black hole if he added an accretion disk. However, there's no evidence that he did so. Okay, moving on to the spacetime foam. Killenson asks, if the quantum vacuum is fluctuating, is this something that could be used to perform work? Sadly not. Although a fluctuation could in principle push, say, a very tiny piston in a particular direction to drive a tiny engine, the random nature of the fluctuations means that you can't know which way that push will happen. And even if it happens to be in the right direction to depress your cylinder, there'll soon be another push that's in the wrong direction. It's the same issue with using the random motion of particles in air to extract energy. If you want to hear the whole story, check out our Reversing Entropy with Maxwell's Demon episode. GLMartin90 has a question regarding the statement that photons in our Heisenberg microscope warp the fabric of spacetime, noting that we typically think of only matter as doing that. So it's true that an individual photon moving in a single direction doesn't warp spacetime in the same way that a particle with mass does. However, if you trap massless photons in a massless mirrored box, then the system has an effective mass which does warp spacetime. In the Heisenberg microscope thought experiment, the photon has to bounce off the object to be measured and back to the observer. Just like in the mirrored box, there's a warping of spacetime between the observer and the object, although it's not quite the same type of warping as you'd get with mass or with a box of photons that are moving in all directions. Flavorful Nuggets 1 has a story to tell. I was walking to class one day when I was at college, and Matt was walking out of my school in the opposite direction. I wanted to ask him so many questions, but the second I saw him, he took the hugest bite of a pastry, so I just gave him double finger guns and said, "Hey, I know you." Thankfully, he gave me double finger guns back, or I would have killed myself that day. Well, Flavorful Nugget 1, thanks for the what's up. I remember exactly where this happened, so I know it might happen again. Next time, say hi, no matter what I'm stuffing into my face.